Good afternoon, everyone. I hope you can hear me clearly. So if you can't hear me, drop me a message and then I will be able to see it here today. So we'll start with our lesson. Now, before we start, we actually need to go over some revision. Actually, last week we discussed how to name certain ionic compounds, and when naming ionic compounds, what rules to follow was discussed. So today we are going to start off with some revision. Now I asked you to complete all the questions in page number 9. I hope you have done it already. So let's see whether you have gotten to these answers. So the very first question is, write the formula of the ionic compounds given below. So we have first one, sodium oxide, right? Sodium oxide. So we have sodium and oxide. So sodium usually forms +1 charged ions. Oxide is a -2 charged ion. So therefore, when you're writing the formula, if you cross the charges over here, so this is -2. If you write the magnitude of the charge right next to sodium and magnitude of sodium charge right next to oxygen, you get the actual formula of the compound, which happens to be this Na2O. Now you need to know this, because moving forward, if you don't know this, it will be a problem and it will be difficult for us to move forward without this information. Then we have written iron sulfide. Actually, in the IUPAC naming system, it will be referred to as iron 2 sulfide because it says containing Fe2 plus ions. So iron 2 sulfide basically contains Fe2 plus ions and oxide, like so. Now, according to the crossover method, we have to write these charges under each other's chemical symbol. But here, since both the charges are the same, actually the magnitude of the charge is the same, they cancel off. We can say Fe2 plus as a +2 charge, 2 minus as, or 2 minus has 2 negative charge. They will cancel off to give us FeO, ferrous oxide. And then C part, we'll quickly do these things, see if you have gotten this right. Cobalt 3 sulfate. Cobalt 3 sulfate. So CO3 plus, and if you take sulfate, we have this charge over here. And then if you're writing cobalt 3 sulfate, you can write the charge of sulfate over here under cobalt and the charge of +3 over here under sulfate. So then this becomes CO2, and within brackets we write sulfate, and the charge of cobalt is written outside of the bracket, which is this. Now this is a shortcut method of getting to the answers. So this is the formula for cobalt 3 sulfate, right? And then we have barium fluoride. Those are easy ones, so I'll directly write barium 2 plus charge, fluoride is 1 minus charge. So therefore the formula will be barium fluoride, like so. That is easy. Copper bromide is also similar. Cu2 plus and bromide is 1 minus. So therefore you get Cu Br2, and then after that manganese 3 plus forming manganese oxide. So that is F, right? Mn2 plus, or actually Mn3 plus. This is a Mn3 plus ion that they have given in this question. Mn3 plus and oxide ion. So O2 minus. We normally don't come across Mn3 plus that much, but this specific question is asking us to write the formula for the oxide of manganese that contains Mn3 plus. So we have to follow through. So then again, charge of oxygen, the magnitude of that is written right next to manganese. Charge of manganese is written right next to oxygen. Mn2O3. Okay, so this is how we get to these answers. There are a few more answers to be written, so we'll do it here. And then we have mercury 1 iodide. So mercury 1 formula is given to us there. So this is the G question. Hg2 2 plus, this is mercury 1, or we say mercurous iron. Last week we discussed this, and then it is coupled with iodide, so therefore we get to Hg2 I2. so this you will have to use a little bit of your logic as well, without depending solely on the crossover method. Now if you take a look at this, we have a mercurous iron which has this formula Hg2 2 plus. Oxidation state of mercury here is +1. Now we need to neutralize this charge. If you are forming an ionic compound, one iodide will not be able to neutralize the +2 charge. You would need 2 iodide ions, then only the charges here will be neutralized. So when you're writing the formula, do it mindfully. Don't just write the formulas using crossover method. Then sometimes when it comes to somewhat unique formulas like Hg2 2 plus, this is somewhat uncommon, right? So when it comes to those kind of parts, you will find it difficult to get the correct answer if you're just mindlessly trying to do the crossover method when it comes to writing any formula. So I would say when you're writing ionic compounds formulas, to be a bit more mindful, especially when it comes to ions like mercurous ions, Hg2 2 plus. And then magnesium phosphate. So that is also quite easy. Magnesium, as we know, is a group 2 element, so it has magnesium 2 plus charged ions. Phosphate PO4 3 minus. So again, you can follow through with the crossover method, and then you get to Mg3 PO4. Outside of the bracket you will have to write 2. Now again, let's observe whether this makes sense. We have magnesium, 3 of them magnesium 2 plus ions, 3 magnesium 2 plus ions, and we have 2 phosphate ions according to the formula coupled with them. So altogether these magnesium ions, they come to +6 charge, and then each phosphate is -3 in charge, so therefore the total charge is -6, and then +6 charge cancels off the -6 or negative charges that are present there, so therefore it becomes 0 in charge. So therefore this formula is also correct. Okay, so these are the formulas that can be written if a name of a compound is given to you, name of an ionic compound is given to you, and if they have asked you to write the formula of the ionic compound, you can use this method, right? So be familiar with these methods. It will be easier for you going forward if you are okay with these parts. If you have any questions, now would be the time to ask. Anyone has any questions? Everyone clear with this? Right. Okay, right, so let me move on. Now there were some other questions as well, writing the names, and I asked you to write the names only of a few because certain parts we haven't covered yet, so we'll get to them fast. So today's class, students, we will be following the usual normal physical class schedule. So we will have a short break in the middle, and then we'll continue on. Otherwise, without our physical students continuing on for directly 3 hours tends to be a bit difficult. So we will make sure to directly go for 1.5 hours, and then we'll take a small break like we usually do in a physical class, and then after that we will move on to the next part. Okay, so one more part. I'll do a few of these because this is also important. So I'll do A, B and E part so that you know how to write these names. Today in the latter parts also we'll be discussing this naming of ionic compounds with polyatomic anions. So at that point also I'll be discussing this in detail. So therefore I'll complete this as I have asked you to write the names of these as well last week, and hopefully you would have covered those parts by now. Now, bear with me a second, students. Right, so after taking this down, you can see sodium ions are now present with chromate ions. I do believe your eyes are now used to seeing the ions that are making up an ionic compound. Now you have to get used to that. You need to know your anions. Without knowing your anions, you will not be able to figure out okay, what are the main two things that are making up this ionic compound. So get your mind used to it. Familiarize yourself with the anions that are commonly used in A levels or commonly seen when it comes to chemistry. So this is a chromate ion. So basically what we have is two sodium ions, two sodium 1 plus ions with one chromate ion. Now you don't have to write it like this. The reason why I am expanding on this and explaining it to you is when you're writing the name of the ionic compound, we always write the name of the positively charged ion, and then we leave a space and then write the name of the anion followed by the positive charged ion's name. So we don't care about the number of ions that are present here. We just write the name of the ion, name of the positive charged ion followed by the name of the negatively charged ion. So the name of this particular this particular ionic compound would be sodium space chromate. Right, sodium chromate. So this represents the sodium ion. This stands for the chromate ion that is present here. Right, so in the IUPAC naming system also we follow this method. So this is sometimes written as sodium chromate 6. That is also correct. And then over here we have potassium ions, right, two potassium ions. You need to see these ions. I asked you to familiarize yourself with this. There was a table given to you right next to these questions, so you can refer to the ions that are present here, right? So this is a potassium ion and this is hydrogen phosphate ion. So the name would go as potassium the name of this ion is hydrogen phosphate. This particular ion's name, if I write it here, the name of this ion is hydrogen space phosphate. So that name itself has a small space in the middle, something to keep in mind, right? So you have to write potassium and then leave a space and then start the name of the anion. Name of the anion is hydrogen phosphate. And if I write lithium, we have lithium carbonate here, we have lithium ions here. Lithium is 1 plus, and we have carbonate ions here, CO3 2 minus. So when you join the name, it will become lithium carbonate. Always only the first letter is capital, no other letter is capital in the entire name. No other letter should be written capital in the entire name, right? So these are the main parts, students, that I want you to get reminded of. Last week we discussed most of these names that we need to know about, and then when it comes to naming ionic compounds, we didn't necessarily go deep into polyatomic ion containing ionic compounds, but I asked you to go through the table here and I asked you to memorize the names. Hopefully after that, since I asked you to complete these tasks, I hope you have completed them by the time that you came to the class today. So we move on to the next important part, students. Now if any of you have any doubts or anything, drop me a message here, or you can just unmute yourself and talk to me today, because we are having a class at different location here, so I can attend to those very easily. Anyway, so now in the next part we are discussing naming molecular compounds. Naming of molecular compounds. Let me erase this first. Now I told you, under inorganic compounds we are going to learn about 4 different types of compounds. First one is ionic compounds, which we are done with, and then second one is covalent compounds or molecular compounds, right? Compounds that are mainly made up of covalent bonds. So that's the second one. And the third one is acids and bases. Acids and bases. We will come to acids and bases today itself. Hopefully if we finish this part early and if you guys answer questions correctly, we can move on to acids and bases easily. And the last one is hydrates. Again, like I mentioned, our syllabus doesn't focus a lot on hydrates. It's a very tiny part. However, it's not something that we are focused on a lot. But still, we'll learn about hydrates and we'll finish the entire naming of inorganic substances. And then afterwards, if we have the time, we are going to move on to amount of substances, or basically we are going to dive deep into the concept of 1 mole, right? Concept of 1 mole. Or Avogadro's number, right? So we'll do that after naming the compounds. Okay, so now when it comes to molecular compound, students, unlike in ionic compounds, we can identify the molecular compounds as simple discrete units, right? So if you take an ionic compound, like let's say we say sodium chloride, what we write as sodium chloride is basically the basic ratio between positively charged ions and negatively charged ions present in the sodium chloride lattice, right? So we say, okay, in this lattice, since it is neutral, the sodium ion to chloride ion ratio should be 1 to 1. So that means our formula should be written like this, right? So that's how we get to the formula when it comes to ionic compound. This doesn't mean our sodium chloride comes as a nice molecule like this, right? There's no individual unit of sodium chloride that you can show and say, okay, this is sodium chloride, this is one single unit of sodium chloride. No, you can't say that. Sodium chloride is a lattice, right? It's a massive network of positive negative charged ions. So what you write as a formula here is basically the ratio between the positive charged ions and the negative charged ions. You can't identify a single discrete unit, okay? However, when it comes to molecular substances, we can identify single discrete units. For example, if you take water, we know this is just a single water molecule. It is not a part of a huge network of something. It's an individual discrete unit, right? Unit that we can separately identify. When I say carbon dioxide, I know I'm talking about this, right? An individual unit, a single molecule can be identified, right? So that is something that is usually seen in molecules or covalent molecules. So then we are going to learn how to name these molecules according to the rules that are given. Turn to page number 10. So page number 10, we can see the basic rules are laid out here. It says the molecular compounds differ from ionic compounds as they consist of individual molecular units typically formed by non-metallic elements. Binary molecular compounds follow the naming convention similar to binary ionic compounds, where the first element is named, where the positively charged element is named first, and the second element has an IDE ending, right? So just like the normal ionic compound naming. For example, I have given you actually these names. the name of HCl molecule, right, which is this molecule. So over here we know hydrogen has a positive oxidation number. So hydrogen is going to be named first, right? We write hydrogen, followed by the name of the negative oxidation element with a negative oxidation state, which is chlorine here. So the name of the negative oxidation state element is going to be modified with the addition of IDE, right? With the addition of IDE. Bear with me a second, students. So we have this IDE ending, just like in ionic compound naming, right? For example, here also, if you take a look at the name of the compound, now carbon is here +4 in oxidation state, these are -2 in oxidation state. So usually we name the positive oxidation state element first, so we just write its name without any change in without doing any changes to it, carbon, then leave a space, and we write dioxide. I'll let you know why we write dioxide. Now first of all, I wanted you to focus on the fact that we end this name with IDE, right? So normally any molecule that is made up of only two elements, usually when you're naming them, the second element's name usually will end with the IDE ending. When you have, these are called binary compounds. Binary compounds are consisting of mainly two different elements. So their name will end with the IDE ending. The first element's name, which is the more positive oxidation state element, will be written without any changes to its name, and the second element's name usually will be written with the IDE ending. Now this name also brings us to another very important point, that is the prefix before the name of the second element. The name of the second element is this. This is the name of the second element. Now what we have over here is a prefix, right? So we have a prefix here. Now what does this prefix tell us? It says with one carbon atom there are two covalently bonded oxygen atoms. So the name of the atom tells us, the first written atom tells us that it is a more positive oxidation state element here, and then the name of the second element is written indicating it is the negative oxidation state element, and the prefix will tell us how many of those atoms are there, right? Usually sometimes even the very first element has a prefix. Now in this case, since there's only one of the first element, when there's only one of the first element, we don't use prefixes, right? The very first element, the positive oxidation state element, there's only one of it. When there's only one of it, when it comes to the very first element, we don't write a prefix. When it comes to the second element, then from there onwards we'll definitely include, even if it's just one, we need to include a prefix. When it comes to the very first element, if there's only one of it, we don't bother including a prefix. But if there is more than one, like 2 or 3 or 4, then we have to include a prefix. So the naming will get clearer as we look into the rules in a bit more detail. So let me do just that, right? So we'll look into the rules, right, so that you will get clear as to how we should do this. So turn to the same page 10. We can see in case where multiple compounds can be formed, Greek prefixes indicate the number of atoms of each element, and then they have given some prefixes here: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So these are basically the prefixes that you are somewhat familiar with throughout the past lessons as well. Mono stands for 1, di stands for 2, tri stands for 3. So all of them are in the table here. And then some examples are given: carbon monoxide, carbon dioxide, sulfur dioxide, sulfur trioxide, so on and so forth. And then under the guidelines, I have just given you very important detail here. When it comes to the prefix mono, and when it comes to naming the very first element of a covalent compound, in the first element, if there's only one of it, right, the more positive element, if there's only one of it, you don't have to use the mono prefix, right? So let me elaborate on that a little bit further. So if you take carbon monoxide, carbon dioxide, we have nitrogen dioxide, and we have this. Let me name these so that you understand what I mean by using the correct prefix. In each of these cases, the very first element holds a positive oxidation state. So the one with the positive oxidation state is always written first. So here there's only one carbon. And what are the prefixes for having one carbon? Like, whenever you have one of something, the prefix would be mono. Having two, it would be, di. So having one of something, we have to use the prefix mono. Having two, we use the prefix di. 3, we use tri. 4, we use tetra. 5, we use penta. Since the rest of it is given to you there in the tube, I'm not going to keep on writing all the prefixes there. So now, according to the rules, we have to write each element indicating the number of atoms of each element in the molecule. So if we just go by those rules, since there's only one carbon here, we have to start the name with monocarbon, and then there's another one oxygen, then write monooxide, monocarbon monoxide. But we very clearly know that's not the name that we have given this. We say this is carbon monoxide. We say this is carbon monoxide. So the word carbon didn't get a prefix mono. Now that is because when it comes to the very first element, if there's only one of it, we don't bother writing the mono prefix for the first element. If there's only one of it, if there's two of it, we have to use it, right? We have to use the correct prefix. But when it comes to having only one of it, we don't have to. So here again, this is going to be carbon dioxide. This is going to be nitrogen. So I didn't write mononitrogen. So this is just nitrogen. Nitrogen dioxide. And again here. Now this one, the very first element, there's not only one of it. There are two of them. Right? So then you can't skip the prefix. You have to include the prefix there. Then you write dinitrogen, because the very first element, now there's not only one of it, there are two of them. So therefore we write dinitrogen, and then there's 4 of oxygen, then we write it as tetroxide. Dinitrogen tetroxide. Is that clear? Do you understand? Right? So if you have any questions, now would be the time to ask. So this is how you would normally write our names. Like, especially when it comes to the very first element, you need to know how to use the prefix. Okay? Right. So then afterwards, after this, actually we move on to the proper naming rules, right? Summary of rules for writing names of simple covalent compounds. So take a look at the summary of the rules. take a look at the summary of the rules and I will explain them further. I'll expand on them. First one, less electronegative element comes first. Less electronegative element comes first, true. If you take a look at all of these compounds, oxygen is more electronegative and the other one is less electronegative. The reason why we say that is just like when it comes to ionic compound naming, when the less, this is the more electronegative element, oxygen is more electronegative, carbon is less electronegative, right? So when you write the less electronegative element's name first, we are basically saying this particular element has a positive oxidation state, right? It resembles the whole naming system that we use for ionic compounds as well. When it comes to ionic compound naming, we always wrote the positively charged ions name first. Similarly, here we want to start with the element that is having a more positive oxidation state. If the second element is more electronegative and this is less electronegative, then what happens? The less electronegative element will get a positive oxidation state. So we want to write the less electronegative element's name first, or in other words, we want to write the more positive oxidation state elements names first. Right, so then write the name with a space between the two elements. Yes, we discussed this. The more electronegative atom's name is modified with the word IDE or suffix IDE. So each of these names end with IDE suffix. So the more electronegative element's name, the name that is written second, gets modified with the suffix IDE. And then the prefixes indicate the number of similar atoms, but mono is omitted for the first element, right? Prefixes indicate the number of each atom that is present in the molecule, and then usually the mono is omitted for the first atom. So if the first atom there's only one of them, we don't bother writing mono, right? We just write the name of the element and move on. And this is very important, right? The last part. Drop the final vowel of the prefix. Underline this is important. Drop the final vowel of the prefix when it ends with a or O, and the second element starts with a or O. So let me explain that without just talking about it. Let me explain what this means. Now normally we have when you're writing a name of a molecule, it could have always the name could have two parts: the less electronegative element's name, the more electronegative element's name. Whenever you are writing any element's name also is broken into two parts, right? So that is a prefix and the name of the element. In certain cases, especially when it comes to the more electronegative element, you will also have a suffix, which is the IDE suffix, but we'll hold on to that part for the time being. So we have prefix and the name of the element. So for example, now when it comes to carbon dioxide, we wrote dioxide. So when you add these two together, we wrote dioxide. Right? When we add them together, we wrote the word dioxide. Apart from that, we have here, we would have come across trioxide as well. TRI, like for example sulfur trioxide, SO3, TRI plus oxide, right? It is written as trioxide. Now the next case, we have the name tetra oxide. Now the last rule I gave you says if the name of the prefix ends with a or O, it could be ending with a or a O, and the next element's name starts with A O O, we actually have to cancel off. The A of a the prefix's final letter has to be cancelled off when it comes to a situation like this. Now if you have a prefix ending with the name with the vowel A O O, and the name of the other element starts with A O O, then the last letter of the prefix is usually cancelled off. So that is what happens over here. So this gets cancelled off, we don't use that, so the name gets changed to tetroxide. So it's not tetraoxide, it becomes tetroxide. Or again, when it comes to writing mono plus oxide, when it comes to carbon monoxide, right, what did we do? Did we write it as monoxide? No, right, we didn't write it like this, right? Monoxide. Did we write it like this earlier? Carbon monoxide? No, we cancel off the last letter of the prefix, and then we join them together and write as monoxide. We write as monoxide. Is that clear? So apart from that, we have pentaoxide. These are some examples, right? Penta. So letter ends with A. So we have these two. If the letter prefix ends with A or O, and then the next element's name starts with A or O, then the last letter of the prefix gets cancelled off. So pentaoxide, you can see ends with A, the next name starts with O. Ends with A, next name starts with O. Here this letter ends with O, the next name starts with O. So still within these parameters. So then here also we cancel off A, so the name changes to pentoxide. So these are some examples. Now you will come across these examples a bit later as well. So these are some examples you need to be familiar with. Is that clear, everyone? Are you okay with this part? I need to know, so you need to show me, at least by raising your hands, you have the option to let me know that you are okay with this. Are we okay with this? Right, brilliant. Okay, everyone. Right, I can see it now. Right, great, thank you. So if you have any doubts or anything, you can now lower your hands. If you have any doubts or anything, you can let me know. Going forward, we can just clear those doubts and move on. So then we move on to some questions that are given over here, and some examples are also there. Carbon monoxide, we'll actually quickly write these here as well for the record, otherwise anyone who looks at this class, who has missed this part, and if you are not necessarily quite sure how these names were obtained, they might get confused. So to eliminate any confusion, let me write the answers here. So for example, if you take some of these compounds that I've written here, H2S, and then we have N2O3, we have H2O, which is water. Water is a common name we use, and then another very good one is P4O6. We have P2O5 as well. It's not given here. I think it's given as a question if I'm not mistaken, so I will not write that. And then we have OF2. I will explain these names. Now usually, now your life is usually made easier whenever we write a formula also, students. The less electronegative element is written first in the formula, right? The less electronegative is usually written first, and the more electronegative element is written later in a formula. That is like a common like thing that you usually see. But if you are not sure, you can see which one out of the two is more electronegative, and then the more electronegative element, their names usually are written later. The less electronegative elements' names are written first. So over here, the very first element is hydrogen, but there are two hydrogens, so we need to show that. So that's why we have written dihydrogen. Dihydrogen, and then followed by just one sulfur. So then we can write mono sulfide. Dihydrogen mono sulfide. Otherwise it will not indicate the number of hydrogen ions. Now in normal use, this is referred to as, in like, you know, whenever you are, this is the IUPAC name, right? This is the IUPAC name. In usual context, let me write it in a straight line, otherwise it's not necessarily going to work for me. So we have the name dihydrogen, space monosulfide. Now this is the IUPAC name, but the common name is hydrogen sulfide. These are just like, you know, common names, trivial names, so don't get too like, you know, upset about the fact that those correct common names are not following a particular rule. Yeah, the only naming system that has very specific rules that we need to follow are usually seen in IUPAC naming system. The common names are somewhat loose, in the sense they don't necessarily have a very strict set of rules. We just have just the naming. Usually we write the name of the less electronegative element first, and then followed by the IDE, and then that's about it, right? So it is not following a proper set of rules, just like the IUPAC naming system. IUPAC naming system follows really good, very clear, very like, you know, clearly outlined set of rules. So therefore the IUPAC naming system is much easier to use. So when it comes to N2O3, there are two nitrogens, so the naming starts with dinitrogen space trioxide, dinitrogen trioxide, and then here we have water. Water is the common name. The correct name would be dihydrogen monoxide. Do you see the O at the end of the name, at the end of the prefix was cancelled off? Whenever you write monoxide, we have to cancel it off. And then we have this one, the 4-phosphorus. So we have to start the name by tetra phosphorus space hexa. Now we can see the name ends with hexa, and then the next part starts with O. Right, name ends with hexa, and the next part starts with O. So therefore, students, the A over here gets cancelled off, and we learned this rule as the fifth rule in the previous part. So this is tetraphosphorus hexoxide. Tetraphosphorus hexoxide. And finally, now this one is again interesting. Now oxygen is known to be a very electronegative element, but electronegativity in the endoperiodic table changes like this. Fluorine is the most highest in electronegativity. That's the first one, right? The highest one. Second highest is oxygen, and we learned the third highest is nitrogen. Right? Then we have chlorine. So FON, fluorine is the most electronegative. So the more electronegative element's name is written second, and the less electronegative element is usually written first, and the oxygen over here is actually having a +2 oxidation state, high oxidation state. Why? Because it is connected to fluorines. Normally oxygen wouldn't get a plus oxidation state only when oxygen is connected to fluorine. No, not any other atom. Only when oxygen is connected to fluorine, oxygen will have a plus oxidation state. So this would be oxygen space difluoride. Learn the name of fluoride correct to write the name of fluoride correctly. It's fluoride, right? Oxygen difluoride, right? Fluoride. Okay, so these are the names. Now I asked you to ask me any questions if you had any. Now what I'm going to do is ask you to complete the question in page number 11, the first set of questions. Write the names of these compounds. Can you write the names of those compounds? And let me know when you are done, because this exercise you need to complete. So complete it and let me know. Let me know when you're done. Hurry up, students. Could I explain the OF2 part again? Right? Yeah, I can. I will. Yeah, it's raining heavily, right? So I understand. That's exactly why we had to do this class online, because many students actually prefer online. So today, for just today, I will do it this way. Anyway, I'm going to explain the OF2 part again. So the rules suggest, right, whenever you are naming a compound, to name the less electronegative element first. No? Okay, so out of the two, if you take oxygen and fluorine, oxygen's electronegativity is 3.5. Now you need to know this, and apart from that we need to just know the trend. We know fluorine is the more electronegative element, then oxygen, and then nitrogen. This is the order, right? Most electronegative element in the entire periodic table is fluorine. So you need to know this. At least the first three you need to know very clearly. So when naming, in the naming system, the rules that I have given you, you can see we are supposed to name the less electronegative element first, and then the more electronegative element second. So over here it's very clear to us the oxygen is the more less electronegative element, and fluorine is the more electronegative element. So the name of the oxygen atom was written first. We just wrote oxygen, its name only. Normally whenever we see oxygen in different compounds, it's the more electronegative element most of the time, but here it's not the case. When oxygen is connected to fluorine, oxygen becomes the less electronegative element, and then followed by the name of the more electronegative element here, which is fluorine. So there are two of them, so we write difluoride. Right, we write difluoride. Is that clear, Nalusha? Is that clear now? Right, brilliant. If you have any questions, feel free to ask. Anyone who's done? If you're done, let me know. You can type in the answers and send me. I will check. Now I know we are joining online, but still it has to be interactive, otherwise no point. Right, so if you're done, send me the answers online, or you can send me the answers on the WhatsApp chat. You can just take a photo of your answer and then send it on the WhatsApp chat, and I'll be able to see. I can access WhatsApp from here. Also, if you're done, can you send me the answers? Carbon dioxide, dinitrogen monoxide, sulfur. Sulfur should be written FUR. The E part is not needed. Sulfur trioxide. See, that's good that you guys send me the answer. So then, if you are making like small mistakes like this, I can highlight those, right? So yes, all the others are okay. All the others are okay. Dichlorine heptoxide, yes. Now I will explain certain parts, like certain issues. Thanks, Rakhitha. So I will explain certain things that you need to correct, right? So others, if you're done, I'll appreciate if you can send me the answers. It'll be easier to move with the class that way. You can just send it on the chat, like, private message me on the chat. That is also available, like, that's also an option that you can use, right? So especially if you want me to comment on your answers, then I can do that here. Dinitrogen monoxide, sulfur trioxide, dinitrogen. Right. So, right, I do see that some of you are making a small mistake here. I will correct that, right? So yes, I see all the answers you have sent me. Thank you. Right. Right. So let me comment on these things. So these are the issues that I have seen through the answers that you have sent me. Now the reason why I like to get your answers is that if one student makes a mistake, then I can talk about it and make sure that none of the others also make the same mistake. So I wouldn't tell any names, of course, don't worry. So, but I want to make sure that all the others also don't make the same mistake. So for example, the very first one is CO2. Now we know the name, I'm not going to do that. N2O. N2O. Some of you missed the oxygen part. When you're writing the oxygen part, you need to make sure you write it as monoxide. You write as monoxide. So the name is dinitrogen space then monoxide. Right? Some of you forgot the mono part. So now hopefully that is something to keep in mind. And then sulfur trioxide, SO3. Now one of the answers I saw, not all of them, just one. Some of you wrote the answer sulfur with SULPHER. That's of course wrong. Even if you wrote it with PHUR, it's still wrong. We usually use sulfur, we write like this, right? So I want you to, sorry, not like this, FUR. I I want to make sure that you write sulfur with F, not pH, right? Not pH, and not like this, not like this also. Either one is wrong. We don't use in our syllabus, we don't like to call sulfur, we don't write the name of sulfur with pH. It is not necessarily wrong in certain other contexts, like for example, you might even find in textbooks sulfur's name written as SULPHUR. However, in our syllabus we specify that we prefer to write it as SULFUR. So therefore, students, you need to follow those steps. It has to be written with the correct spelling. So it's SULFUR. So sulfur, and then we have trioxide. Don't write sulfur with pH. And then we have HCl, right? HCl. HCl's name of the molecule, especially in gaseous state, is easily written like this: hydrogen monochloride. This is the correct IUPAC name, hydrogen monochloride. The common name that we sometimes use is hydrogen chloride. When it is acting as an acid in water, we call it hydrochloric, but that is in water. As a normal molecule of HCl, we call it hydrogen monochloride. That is the correct IUPAC name. Hydrogen chloride is like the common name, right? I told you trivial names are there, common names are there. So this is basically the correct IUPAC name, hydrogen monochloride. And then the next one is fifth one, Cl2O7. So answer here is dichlorine hepta. We have tried Ta. I will just write it and erase it, and then we start with oxide, dichlorine heptaoxide. So we end with the A, starts with the O. So what we do? We cancel the last letter of the prefix. So it becomes heptoxide. It becomes heptoxide. Dichlorine heptoxide. Dichlorine heptoxide. Is that clear? Right. So now, afterwards, students, now we have come to this point. We have learnt about all of this. It is done. Now, what we need to do going forward is make small corrections. Now, some of the answers, some of you were good enough to send me a WhatsApp message with the written answer, which actually was quite helpful, because I saw some of you have done this, like, you know, there was something that has gone wrong here, and you erase that and you write the name there. And sometimes some of you have written something wrong here, then after that you have cut and chop there and then write monoxide or monochloride or whatever, right? So this again would cause you to lose a mark when you are like, you know, writing the answers at the exam. So if you get a name wrong, right, imagine you have some sort of an issue and you get a name wrong, so you cut like this, and then writing the name right next to it like nothing happened over here is a problem. So imagine hydrogen and then space, you left a space, and then you have a, like, you know, small issue, and then after that you write, after cutting it, you write the second name without an issue. If you do it like that, you will not gain marks because you have cut and chop in the middle. You are not supposed to do that. If this happens, just cancel the entire name with a line, right? Here also imagine this entire name, we'll cut it with a line and rewrite the name fresh. Start new. Hydrogen monochloride, right? Or just write it underneath, right? Dichloride heptoxide, right? So don't cut and then continue to write. That's wrong. If you have made a mistake, cut the entire thing with a line and then move on to rewrite the name from the beginning. Right. So then I have given you some names here. And the second part, I've given you some names. Write the formulas fast. Do it fast. Some of you have already done it, I assume, but others, please complete that. And another mistake that I just caught on to while I was going through your answers is some of you have randomly started the second name's letter with a capital letter. That is a big problem, right? I know we make this mistake when you are not initially familiar with the setup, so try to get it corrected, right? So make sure that you don't write the name of the second element. We don't start with the capital letter. If you do that, it's a problem. I have received some answers. Okay. Right. Some answers are okay. Guys, if you're done, send me the answer. CL3P205. Right, I think most of you are done. So we'll quickly discuss that. Write the formula for sulfur hexafluoride. Sulfur hexafluoride, so we have sulfur, one atom. They don't say disulfur, that means only one sulfur is there. Hexafluoride means there are 6 fluorines, so this is the formula, that is correct. Then phosphorus trichloride. Phosphorus trichloride, so we have phosphorus and then trichloride means Cl3, PCl3, and then we have formula for diphosphorus pentoxide. 2 phosphorus should be there, and oxygen number is 5 because a pentoxide, right? So diphosphorus pentoxide is correct, and then nitrogen dioxide, simple one. Nitrogen dioxide is NO2. Right, these are simple. Hopefully you were able to get to these. So students, this is how we usually get to the correct answers. And there's a small flow chart given to you when it comes to the naming of compounds. Hopefully you go through it. It's a simple thing just to help you remember what we have learned so far. So you can go through it. I don't intend to talk about it here because it is basically everything we have done in a small summarized note, right? And then we move on to naming of polyatomic anions and polyatomic ions in general, because there are polyatomic cations as well. So when it comes to polyatomic ions, one thing you need to understand is when atoms are bonded together. Now we are talking about, now this is something that is very crucial to understand. So we have different types of polyatomic ions. Very rarely we talk about a lot of positively charged polyatomic ions. We only have ammonium ions for polyatomic ions, and then we have a whole lot of other polyatomic anions like carbonate, CO3 2 minus, right, and bicarbonate or hydrogen carbonate, right. We have nitrate, NO3 1 minus. We have nitrite, NO3, actually NO2 1 minus. We have sulfate, SO4 2 minus, right. We have sulfite, SO3 2 minus. We have phosphate, PO4 3 minus, so on and so forth. You need to know these ions, right. Phosphate, hydrogen phosphate, dihydrogen phosphate, right. So you need to know these names. Naming polyatomic anions and cations is very, very important, and you need to know their formulas along with their charges. If you don't know them, it will be a problem in the long run, especially when it comes to different types of chemistry. We have different parts where we have to find the concentration of ions. If you don't know how to even take an ionic compound and what are the main component ions of the ionic compound, if you don't know them, it will be a major problem in the future. So familiarize yourself with these ions and take a look at their charges as well, because if you don't know the charge, you can't write the formula. If you don't write the formula, if you don't know how the formula would look like, then when you're trying to calculate the concentration of ions or how many anions are present in a given compound, it will be a problem, right. So make sure to learn all of these names. These are all the names that are given in the textbook. Actually, this table was directly taken from the textbook. So these are the names of the ions. They expect you to remember and memorize. Please go ahead and do that, right. And the other part is, sometimes they ask you questions like this. They ask you what type of bonding is seen here in a given ionic compound like this, right. Sometimes they give you a question like this. If they give you this NH4Cl, they can ask you what are the type of bonding that is seen. So they give you sometimes a table, right. Now this one is in particular very, very interesting. So now if I ask you, let's do that question actually. Can you write it down as a question? Can you write it down as a question? I will give that to you as a question and see whether you understand how to answer this question. Write down. Right. So write down. Consider the following compound. Consider the following compound. And add a tick in front of each of the types of bonds that are seen within this compound. Add a tick in front of each of the types of bonds that are seen within this compound. First one, ionic bond. So if you think it has an ionic bond, please add a tick there. And then covalent bonds. If you have covalent bonds here, you can add a tick. And lastly, we have dative bonds, right. Even if you have one, right, you have to add a tick here, right. So do it and tell me which ones you ticked out of all of these. Which ones you ticked? Okay, anyone quickly? Anyone? Can someone quickly tell me the answer? I haven't received any yet. I haven't received any yet. Is it difficult, this question? Ionic bonds, okay, we have, I think I have received some answers here. Ionic bonds, okay. Nilusha, you had a question earlier, I didn't see this. So Nilusha, you have asked, I didn't see that question earlier. Is it dichloride or dichlorine you have asked? So now here, let me, now while others send me the answers, I will explain this part. So Cl2O7, right? So here, out of the two, which one is more electronegative? Now chlorine has electronegativity of 3.0, oxygen has electronegativity of 3.5. So we always write the name of the element that has a lower electronegativity first, no? So when you're writing the first element's name, we specifically said we don't make any changes to their name. This is a chlorine element or chlorine atom. So we don't make any changes to their name. So therefore what we do is only indicate how many atoms of those are there. So we write di, the name of the element is chlorine. Only time we make a change to the name is when you're writing the name of the second element. Name of the second element always should end with IDE. Here the second element or the more electronegative element is written second. So the name of the second element, we don't write it as oxygen. We write it as oxide. The name ends with IDE. Right? So here we can't just write oxide here. There are 7 of them. So we write heptoxide. So it ends with IDE. So the IDE ending comes only to the second name, never in the first name. So the first name you write the full name, like full name of the element. Okay. So I am getting few answers. Ionic bonding. See, this is why exactly I ask you these questions. Now this is a good question. So let me explain to you. When it comes to polyatomic ions, you need to know how we form the polyatomic ions. So basic structure of the polyatomic ion should be known, right? So you know, when it comes to ammonium chloride, yes, it is an ionic compound. Why? Because we have learned that there is an ammonium ion, there's chloride ion. So between these two guys there is a ionic bond. So yes, it does have ionic bonding. Very good. Ionic bonding exists between in this compound, right? In this compound we have it. And then we have a polyatomic ion. When it comes to a polyatomic ion, definitely if it is a polyatomic, that means more than one atom is there, definitely it would have what? Covalent bonds, for sure. It would have covalent bonds for sure. We can just draw it like this, right? NH4 plus. This is the Lewis structure for ammonium ion, right? So each of these are what? Covalent bonds. So yes, it does have covalent bonds. But don't forget, under dative bonding we learned that ammonia, actually when it comes across an H plus ion, it donates this lone pair. And forms a dative bond. I will draw the dative bond in different color. I'll draw the dative bond in different color, like so. So this is then, now when this bond is formed, the H plus positive charge is basically can be written outside like so, right? So this is the actual formula of ammonia. We can write it like this also without an arrow, because after the dative bond is formed, it appears as if it is any other bond, right? Once the dative bond is formed, we can't figure out whether it's a dative bond or not. But we know that ammonium ions are formed due to the formation of a dative bond between H plus and ammonia. And we have learned about this under dative bond. So definitely you need to know ammonia donates a lone pair to form an ammonium ion. When you're writing Lewis structures, just simply you can write the ammonium Lewis structure like this also, no problem, without indicating a dative bond. But although you don't indicate it, it has a dative bond. For example, imagine someone gave you a t-shirt, like you took your friend's t-shirt and never returned it, right? So whenever you keep wearing it outside, do you go up to everyone and say, how is this t-shirt? Nice, no? Not mine, friends. Do you say that? No, right? Like anybody who sees you wearing that t-shirt would think, it's your t-shirt. Nobody even will think it twice to ask if it is someone else's t-shirt. So just like that, when the lone pair is given to hydrogen to form a bond, it appears like a normal bond. It doesn't, by looking at it, we can't figure out, is it dative? Right? If you take a look at all 4 of these bonds, they appear the same. So by looking at it, we can't say whether it's dative or not. However, we know, right? Like you will know, this t-shirt is not mine. You will know this is someone else's t-shirt. Just like that, we know how this ion was formed. So we know there was a dative bond here. So if a question like this is asked, you need to say, yes, it has a dative bond there. It does have a dative bond. So this compound has a ionic bond between them, and there are just simple covalent bonds and one dative bond. It contains all 3. Okay, so you need to be vigilant, right? None of you said dative. Actually, none of you mentioned that, right? So if there is an MCQ given, now there are in certain papers there are MCQs similar to this, so then be careful. If they have given the option of dative bond, also include that also if the polyatomic ion has a dative bond. If it doesn't have a dative bond, don't say it has a dative bond. Okay, so you need to know your usual dative bonds theory that we have learned. Actually, under the dative bond formation, we have discussed all the important dative bonds. So study those parts and that will be enough. Is this clear? Do you understand? Was it clear? Okay, all good? Yeah, so what I want to say was, initially I just wanted to say you need to know polyatomic ions. For example, if you take sulfate, you need to know their, roughly their Lewis structure also. We have drawn the Lewis structures of these, right? So you are no stranger to these Lewis structures. This is sulfate ion, right? You know that this is a Lewis structure of sulfate. You need to know this. If you don't know this now, or if you can't just quickly get to these structures by now, please know you are lagging behind. That means the trajectory on is not good. If you can't draw it now without having to look at anything, if you have to think a lot to get to this structure now, because we have done the work, we have laid the theory foundation, and there is a part that you should also do as a student, which is applying the theory that we have learned. So if you can't get to this, or if you don't have a recollection of what we have done this, then if you can't draw this as soon as I mention it, then we are lagging behind, right? So you need to make sure that you pull yourself up and come back onto the track, because going forward we will not be giving you enormous amount of time just to draw Lewis structure. Lewis structure part is just a helping, theory part to latter parts that we come across. Later we come across more advanced theory parts. So then knowing Lewis structures will help. Now imagine, to understand the more advanced theory parts, we need this, right? So imagine you don't have a good understanding of this. So the more advanced theory parts will be difficult for you. Okay, so we don't want that. None of you would want that. So please make sure that you don't lag behind. So students, with that, I believe we complete the theory parts related to this naming of covalent compounds, and then this last one was about ionic compounds as well. So polyatomic ions fall into ionic. One more polyatomic related example that I would like to do is ammonium dichromate. So again, this is a bit of a good one, so therefore I will talk about that and then we'll take a small break. Otherwise I'll not be able to go for 3 hours straight. So here, this is a polyatomic ion, this is a polyatomic ion. So this is the polyatomic anion, polyatomic cation, NH4 plus. There are 2 of them. And here we have polyatomic anion, polyatomic cation and anion. So usually the cation name is written first. The name of this part is ammonia. And then which is written as dichromate, right? The common name that we usually use here is dichromate, right? So that is how you would normally write its name, students. So you need to be able to write the name of these compounds easily. So check the spellings also. When it comes to ammonium, always AMM. Always AMM. I have also written with just simple M, but normally ammonium is always written with a double M. Ammonium dichromate. Ammonium dichromate. Right. So that was the last one. Just to give you an idea that there can be compounds made with 2 polyatomic ions, polyatomic cation, polyatomic anion together. Okay. All right, everyone. So take a small break now. Okay, we will start here. Right. So now we move on to the next part, which is actually also quite important, which is acids and bases. So now, if you turn to page number 14, there we talk about the naming of acids, right? Naming of acids. So in the context of acids and bases, the nomenclature of acid is quite crucial according to what we have learned. So when it comes to talking about acids, now if you take HCl, earlier we learned the name of HCl is hydrogen monochloride, sometimes commonly referred to as hydrogen chloride, right? The IUPAC naming would be hydrogen monochloride. But when it is in the aqueous medium, when it is acting as an acid, we can call it hydrochloric acid. So there's a nice diagram over here. I hope you actually refer to it and develop a bit of an understanding. So here, read through this particular text with me so that you understand why we have 2 different names for the same covalent compound. So acids behave differently than other covalent compounds in water. Acids have the ability to release a proton in aqueous medium. So if you take carbon dioxide and dissolve it in water, it doesn't donate protons into the medium, so it is not acting as an acid. But if you take something like HCl, HI, HBr, these are capable of releasing H plus into the medium, into the aqueous medium. When they are present as just a normal gaseous molecule, for example HCl gaseous molecule, it will not release H plus in the gaseous state. However, if you take the HCl and put it into water, then it releases H plus. So as it releases H plus, it is acting as an acid. So an acid is defined as a substance that releases hydrogen ions or protons when dissolved in water. H plus is equivalent to 1 proton, or so often referred to as such. Acid formulas consist of 1 or more hydrogen atoms and an ionic group. Compounds possessing 1 or more ionizable protons. That is important. 1 or more ionizable protons. Right? You need to have ionizable protons. Proton stands for H pluses. right, proton spin H pluses, are referred to as acids, right? So these anions with names ending IDE give rise to acids with a hydro prefix and IC ending. As detailed in the table below, there are instances where the name of the chemical formula seems to have two different names. However, the complete name should end with the term acid. Now let's go with what we see in these tables. Now we can see here, if you take just a HCl molecule, in, let's say HCl in gaseous state for that example, not in aqueous medium, HCl in any other state, will be given the name, the usual name that we looked at earlier. We'll name it as a normal molecular compound, hydrogen monochloride. We can, like, if the common name of this would be hydrogen chloride. However, in aqueous medium, if you have dissolved HCl in aqueous medium, let's say we'll have HClAq, that actually dissociates in water, like so. That means very easily we can say, now this is acting as a acid. Now this is acting as an acid. So if it is acting as an acid, students, then if it is acting as an acid, then you have to name this as an acid. This is acting as an acid in aqueous medium only, not in gaseous state here, which is acting as an acid in aqueous medium. So when you are naming it, their names should start with hydro, according to what we just read. You should start with hydro to indicate the ionizable hydrogen that is present here, and then the name should end with IC, and the final part of the name is acid. Acid, right? So there should be a IC ending, and there should be another part over here as well. So here we have the names given here. This is chlorine, so therefore we write hydrochloric acid, hydrochloric acid. If you take bromine in the same way, HBr, if it is present without being present in water, HBr would be referred to as hydrogen monobromide. But if you dissolve it in water, it will act as an acid, just like this. So therefore it will be referred to as hydrobromic acid. So what is common here is, when it comes to these types of acid, the hydro part is there to represent the ionizable hydrogens that are present in the molecule, and then the anion name is written with the IC ending. Right, anion name is written with the IC ending, not the IDE ending that we usually saw in the previous instances, right? So it changes to an IC ending. Okay, so do you see here? So molecular compounds, the names are basically given as hydrogen fluoride, hydrogen chloride, hydrogen bromide. These are common names. If you name it the IUPAC way, it will be hydrogen monochloride, hydrogen monobromide, so on and so forth. But commonly we refer to them as hydrogen chloride, hydrogen bromide, right? Just like in the beginning of the class today, I talked to you about the hydrogen sulfide. It is hydrogen disulfide, the correct IUPAC name. But commonly, as a trivial name, we call it hydrogen sulfide. So here also, to HCl, we commonly refer to them as hydrogen chloride. So that is when HCl is not acting as an acid. However, whenever HCl is present in aqueous medium, now this is not when HCl is present in aqueous medium, but whenever HCl is present in aqueous medium, it acts as an acid. So their name is no longer hydrogen chloride or hydrogen monochloride. It changes to hydrochloric acid. Hydrochloric acid. So that's a couple of names that are given over here, students. So a few that I would like to specially highlight are these. If you take a look at the last few, right, H2S, and then HCN. Those are a bit important. Now in this table, under molecular compound, what we see is the common names, right? So it's not the IUPAC name. So if you call, the common name for this is hydrogen cyanide, right? Hydrogen cyanide. But when it is present as an acid, the acid name is what? Hydro. This is cyanide, changes its name to Nic. So it's now cyanic acid. It ends with IC now. So it's called hydrocyanic acid. And H2S. Now if you write the proper IUPAC name of H2S, dihydrogen monosulfide, but commonly we refer to it as hydrogen sulfide. This is the common name. And if you write its acid name, it will be hydro. Keep in mind there's a hydro part, and then write sulfuric acid. Now this is not the normal sulfuric acid we know of, okay? This is not the sulfuric acid that you know of. This is hydrosulfuric, right? Hydrosulfuric means we are basically talking about H2S in aqueous medium. H2S in aqueous medium is referred to as hydrosulfuric acid. So don't confuse this with sulfuric acid, which is H2SO4. There's a, I will clarify that. So we commonly refer to H2SO4 as simply sulfuric. We call it sulfuric acid. This is not hydrosulfuric, this is just sulfuric acid, right? This is a common name. And what you see here is the name, IUPAC name for the acid that is written over here in H2O. So basically when H2S is present in aqueous medium, we call it hydrosulfuric acid. Is that clear? So see the distinction here. These compounds, they can show that it is able to act as an acid when they are present in water. Why? Because the definition of the acids that we are discussing over here is molecular compounds that are capable of releasing H+. Molecular compounds that are capable of releasing H+ in aqueous medium. Right? So therefore students, over here, these, when they are present in gaseous state, they don't go around releasing H+. Right? H2S gas doesn't, like, as it moves around the atmosphere, doesn't release H+ anywhere. Right? But when it is present in water, like in the diagram here that I have given, it releases H+. Now this diagram, if you are wondering what in the world is going on in that diagram, usually students, we say, now imagine you have HCl here, we say the water molecules, they get the H+ that is released over here. So okay, so what happens is there's lone pair here. These lone pairs are given to this hydrogen to make a bond, and this HCl bonds break, and then they form hydronium ions that look like this. There's a lone pair here. So this hydronium ion will have a overall plus charged along with a Cl minus ion. So instead of just saying H+ is released, we are now showing it in a much fancier way. Like what is actually happening is this, right? H+ is released. But normally we don't say just H+ goes out into the water without anyone assisting it. We just mention H+ is given to water, right? H+ is taken by water, forming hydronium ion and chloride ion like so. So keep in mind, we normally are capable of writing H+ ions that are coming into the medium like this, H3O+. Right? We can write H+ that comes into the water as H3O plus, or plain and simple H plus is also fine. In other words, H plus is equivalent to, these three lines are shown to say it's equivalent to H3O plus. They are both the same thing, right? They are both the same thing. Okay, so here this indicates the water molecule comes and takes the H plus, or water molecule is given the H plus by HCl and forms H3O plus and Cl minus. Here we are talking about the fact that HCl breaks forming H plus and Cl minus. Here there is no mentioning of water, but this only happens in water. This doesn't happen in any other state. So therefore we basically mention both of these are the same. We just say both of them are the same. We need to understand H3O plus is equivalent to H plus. Okay, all right. So are we clear? So read the text under the diagram, please. When dissolving in water, HCl molecule is converted to H plus and Cl minus ions. H plus ions associated with one or more water molecules and are usually represented as H3O plus. So H plus, normally they get connected to one or more water molecules, usually one water molecule like so, and then they form hydronium ions, H3 plus, H3O plus ions. Right. Okay, is it understood? So remember the names. Hydrogen sulfide is turning into hydrosulfuric acid. HBr is hydrobromic acid, and then we have HI is hydroiodic acid, right? So hydrofluoric acid. I need you to remember these names. They are all given in the tute. Hopefully you are referring to the tute as we speak. Okay. Then we come to the most important part when it comes to naming acids. Many students after a while forget about these parts, right? So naming of acids break into mainly two parts. Usually an acid has two sections in it. Okay, if you take an acid, it has ionizable hydrogen and an anion, right? So basically it has the ability to release H plus, and the rest of the acid becomes an anion. Right? And then this also was broken into two different types of anions, right? Ones that we discussed, like the anions without any oxygen in it, right? We can say anions without oxygen in it. And then we have anions that contain oxygen in it. So these are referred to as oxoanions. They are referred to as oxoanions, right? So the naming of oxoanions is what we are going to be looking into next, right? So if you turn to page number 15, right? Turn to page number 15. So oxoanions are contained in acids that are referred to as oxoacids, right? So keep in mind, if you have oxoanions, those kind of acids are referred to as oxoacid. Makes sense, right? If you have oxygen in the anion, we call them oxoanions. If you have oxygen in the entire acid is containing the anion plus hydrogen, so those kind of acids are referred to as oxoacids, right? So naming of oxoacids are usually following a few rules, or we need to know the basic outline of these rules, I feel like you will feel a bit more confident after you go through this part. Because one of the issues many students have is they don't know how to name these complex acids and all that, and we usually come across these complex acids and they get confused, or you all most probably will get confused if you don't know the naming system. So that's what we are trying to do here. We are trying to eliminate that worry, and we are trying to get you to properly name all the complexes, or not complexes, all the compounds that you come across. So they say oxoacids are a category of acids containing hydrogen, oxygen and other elements. In other words, compounds with one or more ionizable protons in aqueous solutions and anion with oxygen are called oxoacids. So the anion with oxygen, anions with oxygen, right? So basically oxoacids, now these form oxoacids, right? Oxoanions, when combined with H plus, they form the acid. So the acid is basically a oxoacid. So oxoacid formulas typically start with hydrogen followed by central element and then oxygen. Few common oxoacids are given below. Basically we have carbonic acid, we have chloric acid, we have nitric acid, phosphoric acid, sulfuric acid, right? So basically all of these contain oxygen. Now this is a oxoanion, and we have H pluses combined together, and what we have is a oxoacid, H2SO4, right? So here when naming this, we don't use the hydro part, right? We don't have hydro ic. Those kind of parts are not there, right? We just call this sulfuric, right? There are basic naming of the oxoacid should be known. The basic root name should be known for you to derive the other name. So if you don't know the basic root name, this is sulfuric. So if you don't know the basic root name, it will be difficult. So we'll cover those today. So then they say these acids serve as a reference point for naming oxoacids, and then some oxoacid diagrams are given here. For example, nitric acid formula is given here. We have the central atom nitrogen, and then we have oxygens. The two are either side like so, right? This oxygen is negative, this is positive. So this is, the charges are not shown here, students, but charge should be shown like this when you're doing Lewis structures. So because nitrogen can't have another bond, otherwise if we could have had another bond here, then the charges will be not present on atoms like this. If nitrogen could form a double bond, additional double bond, but nitrogen can't, it can only have 4. So therefore we stop here. So this is an oxo acid nitric, right? So you can see central atom and then the other oxygen atoms and ionizable hydrogen. So any oxoacid have a central atom bonded to oxygens and ionizable hydrogen. Usually the ionizable hydrogen is bonded to an oxygen, right? Usually in the sense all the oxoacids you come across, the ionizable hydrogen is bonded to oxygen. So then in cases where 2 or more oxoacids share the same central atom but differ in the number of oxygen atoms, the specific rules govern their nomenclature. So this is important. So for example, they have said the addition of one oxygen atom is termed per IC acid. For instance, adding one oxygen to chloric changes the hydrochloric acids to perchloric acid. So first of all, let me draw what this means, right? This is something we need to be very clear of, right? So I will not dwell a lot on this. I will move on to the other parts, but I want to talk about this section. So this is something that we learned. This is called chloric acid, H3Cl O3, right? This is called chloric. I'll write the name here. Now imagine us adding another oxygen atom here. So this becomes actually not H3 here, sorry, HClO3. So this becomes HClO4. Now we don't add it, there are acids with an additional oxygen like so here. So the name changes to perchloric acid. Right, so here the only thing that we had over here was the IC ending, but apart from the IC ending, when it comes to this, we have per part and IC ending. And if you subtract just one oxygen, right, taking one oxygen away to form, let's say, something like HClO2, this is referred to as chlorous, right, OUS ending. Just like can you remember when we were talking about ferrous, the one with the higher oxidation number got IC ending? Just like that, here actually this chlorine is at a lower oxidation number now. If you count, you will see. Here this is at a bit of a high oxidation number, right? So here the difference between these two is IC and OUS ending only. So this is referred to as chlorous acid. And if you subtract two oxygens from this is the reference point, students. This is the reference point. The chloric acid is the main acid. So from there, if you take two oxygens, then you get to HClO. From here to here is just one more oxygen, and that is called hypochlorous acid. So here we get the prefix hypo and ending OUS. So both of these have the OUS ending, right? Two has OUS ending, two has IC ending. The one with the highest number of oxygen gets the prefix per. The one with the lowest number of oxygens get the prefix hypo. But to name any of these, you should know the reference acid. Usually we talk about these. Now here in the previous case also we have discussed, these are basically, these acids serve as reference points to the naming different chemical species. So you need to remember these names such as carbonic, chloric, nitric, phosphoric and sulfuric acids, right? So when it comes to chloric acids, we can see all of these different names. So if you want, I know there is a small table given here, but I would recommend that you take this as well. Otherwise, sometimes you might feel confused when you're referring to them later. Can you please complete these? We have to know a little bit about the anions as well. So if you take this, I will write the anions here. Anions. So if you take this, when the dissociation happens, we have H plus ion along with the anion ClO4 1 minus, right? Here this also can do that. H plus will be removed, so it will form ClO3 1 minus. Here if I just write it like so, we have H plus and then ClO2 1 minus, and this one will be the same. We have H plus and ClO1 minus. So their naming of these anions are also important. First of all, if you have chloric acid, the anion formed is referred to as chlorate anion. chlorate ion, right? Chlorate ion. So therefore this is going to be referred to as per. Now this is perchloric acid. The only change is the ending changes from IC to ATE, chlorate ion, right? So here now we have what do you call it, IC ending turning into ATE, but OUS ending usually turns into ITE. So the ion over here is referred to as chlorite ion. So here the name was OUS. When it is turning into an ion, students, the ending changes to ITE. When there was an IC ending, both of them were ending with ICE, their names changed to ATE ending, right? So it changes to chlorate and perchlorate, and here this guy's name changes to from chlorus to chlorite, right? The ITE ending. So here also we have a OUS ending. So therefore the name here for this ion would be what would it be? Chlorite. Hypochlorite ion. Hypochlorite ion. So this is something to keep in mind. Always when you are converting a ion, so when you are converting a acid to its anion, the anion's name. So imagine we are talking about acid turning into an ion. So the name of the anion, when it is changing, only thing that changes in the name of the anion is that if the acid name is ending with IC, then the anion's name should end with ATE. If the acid name is ending with OUS, the name of the anion is ending with ITE. Now you know this already. For example, some of you would know this very well because we have done questions related to this. What is this? We call this sulfuric, right? And then when it comes to sulfuric acid, we have another version of this with a low amount of oxygen, right? So the number of oxygens here is less. So this is the reference point. That's why we know this name very well. This is a reference point. So from there, one more oxygen is less, right? So this is the reference point in this case. When one oxygen is removed from there, what do you get? The name of this acid changes to sulfurous acid. Sulfurous acid. So these are the main two acids of this particular oxo acid. So these are the ones that we get, not the others. So then if you're forming its anion, let's say this SO4 minus, its name, some of you might not see it there, so I will write it here. Its name is sulfate ion, ending is ATE. IC acid, IC ending gives rise to an ion with ATE ending in their name. Sulfurous has these ions, SO3 minus ions. So their name would be, now it has OUS ending. So OUS ending gives rise to an anion with ITE ending. So this is going to be sulfite ion. Sulfite. Is that clear? Right? So students, these are parts that we need to be familiar with. So if you want, in page number 16, we can actually write down the anions of a oxo acid like this. So this chloric acid has the entire set of acids, like going from perchloric all the way to hypochlorous. But like when it comes to sulfuric, we talk about only sulfuric and sulfurous. when it comes to nitric, we talk about nitric and nitrous. Actually, when it comes to phosphoric, we can talk about three. Like we have phosphoric, phosphorus, and hypophosphorus. Those acids are there, students. So you can talk, not all the oxo acids have all four. Okay, don't expect sulfuric also to have all four of these, right? So sulfuric mainly has sulfuric and sulfurous types. It doesn't have this persulfuric and hyposulfurous parts. We don't necessarily talk about those. Is that clear? Any questions? There's a question, I think. Bear with me. Okay. No questions. Any questions up to this part, students? Anything that you would like to get clarified? Right. So let's try and write the names of these. I want you to be able to write the names of these. I will give you two questions. So for the time being, write the names of these. H3PO4, H3PO3, H3PO2, and then HNO2 and HNO3. Write the names of these acids fast. Write the names of these acids. So you need to know the reference points for each of these acids. I have given them in the tube, so you can see there are 5 acids that are given in the tube, and I have mentioned under them that these are the reference points. So keep them in mind. Phosphoric acid, and then we have here one less oxygen here. Now this was the reference point, students, even in the tube that I have given you. So one less oxygen here, so this becomes phosphorus, phosphorus, ROUS acid, and there's one less oxygen from there onwards as well, so this becomes hypophosphorus, bear with me, OUS, phosphorus acid. So here when you're writing phosphorus, be careful not to use US, it is OUS. This is an acid naming system. So in the acid naming system, we use IC ending or OUS ending, right? For the ones that have the lowest number of oxygens, so these are the ones that you usually have lowest number of oxygens of, so their names should end with OUS. Here now I have changed it up a bit. This was a reference point, right? This is called nitric acid. There's no hydro party or anything, so this is just called nitric acid. So there's an IC ending, right? So in this case, this one has one less oxygen here, so this is going to be nitrous acid, OUS ending, nitrous acid. And then if I just quickly write the anions as well here, just to give you an idea about the anions also quickly before I move on to one more question. Here this has the IC ending, and then I know the anion that is formed over here after the release of H pluses is PO, PO4 3 minus. So therefore what we form here is phosphate ion, right? And then we form over here phosphite ion and hypophosphite ion, right? So phosphite ion and hypophosphite ion. I'll quickly go through these parts, students, because otherwise I will not necessarily have the time to move on to the other parts. So what is the time? Bear with me a second. Yes. Okay. I want to quickly tap into the naming of compounds that contain these as well. So we'll finish off the naming part today. There's 2 more sections. I'll quickly do them after this, like the naming of bases as well as the naming of hydrates. So simple parts, but I would need some time for those as well. So hopefully can get a small intro to 1 mole, the concept of 1 mole, so that you can go home, your home actually, at home you can think of this and develop a better understanding of what 1 mole is. So we have nitrous acid, so it forms nitrate ions because in this case nitrous, so the anion's name would be nitrite, and the cation name would the next one's anion name would be, so we have nitrate here, we have nitric acid IC ending, so the anion's name would be nitrate, right? So these are the names of the anions that you can form. Phosphoric forms phosphate ions, phosphorus forms phosphite ions, and hypophosphorus forms hypophosphite ions. Okay, so these are the main parts that I wanted you to be familiar with. Quickly, let's do 1 more question with bromine in it, and then after that we will finish it up. This is quite similar to the previous set of acids, just to get you to know the naming system a bit better, or familiarize yourself with the naming a bit better. I want you to label each of these anions and the acid names correctly. So after that we move on to the next part. Right, quickly complete this. Now this is the reference point. Understand how we got there. This was very similar to HClO3. HClO3 was the chloric acid. So this is called bromic acid. Right, so we are going to start from here. Right, so these are all halogen based oxoacids. So therefore whenever you see 3 oxygens coming to them, that will be the oxoacid for these bromic acid, chloric acid, iodic acid. So they are always having 3 oxygens connected to it. So when it comes to other acids, for example sulfuric, phosphoric, the number of oxygens that are connected to them is different, right? So this is the starting point. This is called bromic acid. This one, there's 1 more oxygen, so therefore this is called per-bromic acid. Per-bromic acid. This is 1 less than bromic acid, the reference point, so therefore this is referred to as bromous acid. And this is called, and there's even 1 more less, this is called hypobromous acid. Hypobromous acid. This is called, now this ends with IEC, so therefore the name of this anion should be per-bromate ion, and this is going to be bromate ion, and this is going to be, let's say, bromous, OUS ending is there, so therefore here These ions name end with ITE. So this is bromite ion, and this is going to be hypobromite ion. Ending is ITE here. Okay. So just to give you an overall idea how we use these. Now, for example, if I come across something like this, NaClO3. So now I identify the ClO3 ion came from chloric acid. So this is chlorite. This ion's name is chlorite. And this is sodium. Sodium's name is written here. Sodium. So this is how the name is written. Sodium space chlorite. Not IDE. Sorry students. Not chloride. I have written chloride here. This is coming from chloric acid. So therefore this is going to be having the ending ATE. Chloric acid based anion has the ending ATE. So this is called sodium chlorate. Now if I am given another acid like this, let's say I was dealing with hypochlorous acid, which is HClO acid. I know its anion would look like this. This cation is here and the anion is ClO. Now imagine I made an ion. Now what is the name of this ion? This is called hypochlorite ion, right? So if I am given a compound like this, NaClO, so sodium's name is written first, so this is sodium, and we know the name of this anion over here, ClO, is hypochlorite. So this is sodium space hypochlorite. That's the name, sodium hypochlorite. Is that clear? Is there any questions stemming from these? Do you have any issues from these? Hopefully, if you are not clear, let me know. Bear with me, there's another. So acids, why don't we hydrogen in writing as trihydrogen? Right, so bear with me a second. This is why don't we use hydrogen in writing? I'm not, Nilusha, I don't understand the question. In acids, why don't we use hydrogen in writing HNO3 and trihydrogen in? So are you asking me why do we have 3 hydrogens in phosphoric and 1 hydrogen in nitric? Is that the question? Is that the question? So there was a question asked, why is the formula for nitric is HNO3 and formula for phosphoric is H3PO4. So it has to do with the Lewis structure. So when it comes to nitric acid, the Lewis structure is this. Nitrogen is bonded directly to oxygens. So nitrogen is bonded to oxygens like this. There are 3 oxygens here. The nitrogen can only form 4 bonds. All 4 of those bonds are given to form bonds with oxygens. And one of the oxygens is connected to hydrogen like so. Right, so this is the Lewis structure of nitric acid. Right. Okay. So when we are basically putting formal charges, you can see we have a formal charge on nitrogen here and oxygen here as well, so that's something to keep in mind. overall acid molecule is neutral. The formula here, if you count the number of atoms, is HNO3. If we take phosphoric, we have one double bonded oxygen here, and then we have other oxygens like so. So we have hydrogen here connected to each of these oxygens. Right, so these are ionizable hydrogens. Right, these are ionizable hydrogens. When it comes to now we talk about phosphoric as well as phosphorus acid, right? Phosphorus acid. So that is also something we need to keep in mind. Phosphorus can form multiple bonds. So usually they end up forming around 5 most of the time. So here the ionizable hydrogen number turns out to be only 2, although there are 3. Now we write it as H3. That is why earlier I didn't write the anion here, because I didn't want to complicate your understanding. But since you asked about the Lewis structure, now we discuss the Lewis structures here. It should be clear to you. So when this is forming an anion, only these hydrogens are leaving. When they leave, now 2 oxygens over here get negative charges. So the oxygen hydrogen bonds break, H goes as H plus, bond electrons go to oxygen. So therefore oxygen become negatively charged here, same here. Now this hydrogen can't leave because it is not bonded to oxygen. So this is H3PO3, this is H3PO4. Just see, when you ask questions only we discover these things. Okay, and I believe I gave you another one, so I will talk about that also. Some of these acids are not very stable, but for the sake of our exercise that we had to do here, I had to give you some questions. So this is H3PO2. Right, so this was phosphoric, phosphorus. This is hypophosphorus acid. So when it is forming an ion, this bond breaks, and the anion's formula would be anion. I will write the anion here. Anion would be like this. Negative charge is there on the oxygen. So this is basically the anion's formula is H2PO21 minus. So that is called hypophosphite ion. So these are basically the Lewis structures of phosphoric, phosphorus and hypophosphorus acids. And whenever these H hydrogens leave here, imagine this bond breaks when hydrogen is leaving as H plus, then this oxygen becomes minus. Then when this hydrogen leaves, this oxygen becomes minus, and this is going to be the anion, oxoanion. Okay, so you need to have an understanding of these things moving forward. Okay, so good thing that you asked that question, because then we're asking why do we have write as phosphoric acid, not write in trihydrogen phosphoric? No, okay, so that's a good question. So it's a naming convention. It's a naming convention, meaning we have developed certain set of rules as to how we should name oxo acids. So when it comes to oxo acid naming, the acid that is having these oxygens and hydrogens in it, those acids we have given a specific naming system. In that naming system we don't mention any hydrogens there, like in the name there's no word hydro or hydrogen or trihydrogen part is not there. Is that clear? When it comes to the other acids that do not have oxoanions are containing the hydro part, even there we don't tell how many hydrogens are there. We just say hydrofluoric, hydrochloric, hydrobromic. That's it, right? When it comes to H2S, there are 2 hydrogens that can be ionized, right? Hydrogen sulfide. There are 2 hydrogens that can be ionized, but we say hydrosulfuric and we stop it there. We don't say how many hydrogens are attached there. This is due to a naming convention. We have rules we need to follow, right? So in the naming of acids, the rule is, if it is an acid, first of all we identify what acid is. Acid is a substance that is releasing H plus in aqueous medium, right? So when they are not present in aqueous medium, we usually use the other naming systems that, like, are associated with naming compounds. But when they are present in aqueous medium as an acid, then we have our own way of naming acids, right? Acids without oxygen in the anion, or acids without oxygen in it, are named with the hydro part in the beginning, and at the end of the name of the acid we have IC acid part, IC space acid. So that's why we learned about chloric, hydrochloric, hydrobromic, hydroiodic, and hydrocyanic and hydrosulfuric acids. We learned about these acids in the beginning of the naming of acids parts. And then we went into oxoacids. So oxoacid naming is completely different. We have a different set of rules. We say, we don't actually mention the presence of hydrogen here. We don't say hydro at all in the name, right? So we have some reference names and the formulas of the reference acids, right? For example, we need to know the formula of nitric, phosphoric, sulfuric, chloric, and carbonic. So these acids, their general formula you have to know. And from there only, if you come across an acid that has a little bit of a higher amount of oxygen than the reference acid that you are familiar with, then the name changes to per IC acid, right? For example, chloric acid formula is H3PO, so H3COO3. But if you came across another acid that has one more oxygen in it, like H3, not H3 actually, chloric acid is HClO3, not H3, HClO3. So if you have an acid HClO4, there's one more oxygen there, so the naming changes from chloric to perchloric, right? So that is the rule, right? So you are asking me why we haven't mentioned, because we have a different naming system applied for oxoacids. So the naming convention governs it, not that, like, we have anything to do with it. When it comes to naming things, once the set of rules are set, we stick to it, and that's how it usually works. Okay, is that clear, Nirusha? Right. Okay. Right, so we'll quickly move on to naming bases. Naming bases, I don't have anything to say, students. Actually, it's quite clear, the text that is present here. A base is defined as a substance that produces hydroxide ions in the medium when dissolved in water. Examples include sodium hydroxide, potassium hydroxide, barium hydroxide, so on and so forth. So basically, we write the name of the cation followed by the hydroxide part. Name of the cation followed by the hydroxide part. Right? So name of the cation and the anion. You write them together. That's it. Nothing more. Ammonia, even though a molecular compound in gaseous state or pure liquid state, it is also considered to be a common base. Despite not containing hydroxide ion in structure, ammonia yields NH4 plus and OH minus ions when dissolved in water, aligning with the base definition. So students, although we consider, now I'll quickly say the naming of bases, the basic details here again. So when it comes to naming bases, it's just like naming ionic compounds, nothing more. You write the name of the cation followed by the name of the anion. For example, NaOH. We know in water it can release OH minus ions. That's why it is called a base, right? What is the name of the cation? I will write the name here, sodium. What is the name of the anion? Hydroxide. Right? So again, if you take calcium hydroxide, the name of the cation is calcium. Name of the anion is hydroxide. Do we mention how many hydroxide ions are present here? No. When it comes to ionic compounds also, we didn't mention that, right? So this is called calcium hydroxide, and we stopped there. And then we learn ammonia is a weak base And although there are no hydroxides in ammonia, in water it can act as a base. So we are going to learn how it acts as a base in water. So if you take ammonia, students, there's a lone pair here, there are hydrogens here, right? The nitrogen over here is partially negatively charged and these are partially positively charged. And if you take water, right, we have water molecules here. In water we have this situation, hydrogens partial positive, these are partial negative. So I told you, nitrogen can donate these hydrogens to, this lone pair of electrons to form a bond with nitrogen and hydrogen. So since hydrogen can't keep two bonds, it breaks this bond and its electrons are given to oxygen. So when that happens, students, we form this ammonium ions. So there's a hydrogen that got connected to nitrogen. So this is a dative bond. This is our ammonium ion. And when this bond electrons go to this oxygen, oxygen becomes negative. So we have hydroxide ions. Right? So this is what is referred to as ammonium hydroxide. Ammonium hydroxide contains ammonium ions and hydroxide ions. Ammonium ions and hydroxide ions. Together we form ammonium hydroxide. Is that clear? So what we know as ammonia, especially if you have written it as aqueous ammonia, and gaseous state ammonia doesn't act like this. Aqueous ammonia is basically equivalent to ammonium hydroxide. Right? We can say they are somewhat equivalent to ammonium hydroxide, because in the aqueous medium, not all of ammonia, most of them undergoes this change. It releases hydroxide ions and turns into ammonium ions and forms ammonium hydroxide due to this reaction. So therefore we can say ammonia is also something, when added to water, that releases hydroxide ions. So ammonia is also considered a base. So when it is in aqueous medium, what they actually form is this, which is referred to as ammonium hydroxide. It is referred to as ammonium hydroxide. So I would recommend that you take this diagram somewhere, especially in your, in that area if you can, because I don't want to separately give you a note on this. This is more or less common knowledge that you should have as we move forward. So I have given you a small detail there. I basically have given you the note. So despite not containing hydroxide ions in structure, ammonia yields NH4 plus ions and hydroxide ions when dissolved in water, aligning with the base definition, meaning it acts as a base. So what you have to do is, if you want further explanation as to how ammonia turns into ammonium hydroxide, take this diagram down, right? This and this, this and this. Take it down, please. Right, while you take that, I will erase this part. So naming of bases is nothing too difficult. Now this ammonia part was an additional part. It is not necessarily coming under naming itself, but we need to know why we call ammonia a base, because it aligns with the definition of a base. Definition of a base is a substance when dissolved in water, if it releases OH minus ions, it is a base. right? So this one releases OH minus ions, so it is a base. And then basically naming hydrates. So students, there are some compounds in solid state, they have certain amount of water attached to them. Now this is a very famous one, copper sulfate, right? In the lab we actually usually get two different types of copper sulfate, right? We get two different types of copper sulfate. One is blue in color. One copper sulfate crystals that you actually come across are blue in color. The other one is white. So the blue color copper sulfate is actually referred to as the hydrated copper sulfate. Hydrated copper sulfate means it contains certain amount of water in the crystallized form. We call this water of crystallization, right? So we have some water even in the solid state. Now this is a solid, this is not a liquid. You can take it as a powder, it's like sugar crystals. You can take it, right? So it's not a liquid. So in that solid state, 5 water molecules are attached to each copper sulfate. So we name this as copper sulfate. If you're writing the common names, you can just write copper sulfate pentahydrate. Copper sulfate pentahydrate, or else we can just say copper 2 sulfate pentahydrate. Copper 2 indicates that this is +2 charged. Copper 2 sulfate pentahydrate. Penta stands for 5, hydrate stands for water, right? Pentahydrate. Now if you take this copper sulfate pentahydrate and heat it, when you heat it, all of the water actually gets removed, they evaporate, and then they form what is known as anhydrous copper sulfate, right? Copper sulfate. Here this is the IUPAC name, or would be copper 2 sulfate, right? Or the common name is copper sulfate. Common name is copper sulfate. The IUPAC name would be copper 2 sulfate. So usually we refer to them by the common name when it comes to most of our settings, but you should know the IUPAC naming system as well. We have learnt about it. So the IUPAC name is copper 2 sulfate. If it is just the common name, I have written it here, it's copper sulfate. So if you just write copper sulfate, we are talking about the anhydrous form. If you want to specifically refer to the hydrated form, you can say hydrated copper sulfate, or sometimes we have 5 here, sometimes based on how many water molecules are attached to each copper sulfate, it could vary, but most commonly copper sulfate is attached to 5 water molecules. In questions they will give you the number of water, or else there will be questions that are done that asks you to calculate the number of water molecules that are present here. That also comes under unit 3. Basically you carry out calculations. It's very simple. For example, you take a known mass of this, and when you heat it, you get to this particular anhydrous form of copper sulfate, and based on the mass of the anhydrous copper sulfate and the mass of the water that evaporated, you can find out for each copper sulfate how many water molecules were attached. So there are questions that are designed that way. So then later on, after you get to the final answer, you can even name the copper sulfate compound here. If you have 5 water molecules, the name would be this. Okay, so that is how the naming of hydrates go. If there are 5 here, it will be pentahydrate. If there are 3 here, it will be a trihydrate. If there are 4 here, it will be a tetrahydrate. so on and so forth. And some examples are given there. I believe the hydrate naming part is quite simple. There's nothing very complicated about it. But one thing that I would say is, the reason why I got this example also is sometimes in questions this is directly asked. So the hydrated, this is something important, so maybe remember it. The hydrated form of copper sulfate is blue in color, and the anhydrous means no water. Anhydrous means water removed, no water. Anhydrous copper sulfate is white in color. Hydrated copper sulfate solid is blue in color. Anhydrous copper sulfate is white in color. So these are the details that you require before moving on to the next part of our lesson. Now I will not move on to the next part of our lesson now itself, but we will stop the class here. We will be moving on to one more later without moving on to it now itself. Any questions, everyone? Any questions from what we have done so far? All good? Everyone is okay with whatever we have done? Okay. So then we'll stop the class here, everyone. I'll see you again next week, hopefully under better circumstances, under better weather. So I'll see you all again next week at the same time. Right. See you guys.